Hello. So we are continuing our work with inequalities in this section. So in the previous two sections, we looked at solving inequalities, like algebraically, exactly, where we had linear and quadratic inequalities. So we looked at the methods for that. But in this section, we're going to look at inequalities graphically. So when we plot certain curves and functions on a graph, we can use those curves to work out inequalities. So perhaps when one curve or one function is bigger than the or less than the other, and we can use inequalities to represent this. Okay. So basically, in this section, we're going to look at graphically solving inequalities, particular types of inequalities anyway. And so what we're going to look at in this section is actually when you have two functions, f of x and g of x, uh, if we plot these two curves, again, they can be just any given curve, doesn't matter what exactly. We can establish by looking at the graphs of these two curves, right? Fx, g of x, if when one function is less than or less than or equal to, or vice versa, greater than or greater than equal to, by looking at the positions of the two graphs. Okay, so what do I mean by this? Uh, so let's have a look at this graph here. So I've drawn two given graphs, f of x and g of x, on this example here. Again, I'm not being too detailed because hopefully I'm just trying to illustrate the idea here. But again, this idea will apply to any given graph. But let's have a look at this, right, to illustrate what's going on. So let's examine exactly what happens across all values, right? So if we move from left to right, so imagine this is the x-axis and this is the y-axis. What happens if we move from the left of the x values to the right and then beyond, right? What happens to the two functions, as in where kind of what values, what position they are in on the graph. So let's have a look then. So hopefully you notice that f of x here, the red curve, goes up as we go from left. It goes up. It's coming down, right? So if you imagine it's off the chart, it's off the graph, it's off the page here, but then it goes down to when they intersect at this point here, and then we move to the left, and then we keep moving, sorry, to the right until they intersect again at this point here, and then they go the separate ways again. Okay, and into infinity. Okay, let's. But what I want to look at then is actually w- how the distance or the position of the two different functions. Okay, so what do I mean by that? Well, what happens before they first cross over at this point here, the first point I've circled. Okay, I'm going to call that point one. Okay, I'm going to call this point two. Okay, so before they reach point one, again, it helps to draw that to extend the graph a little bit. Before we point one, hopefully you recognise f of x, the red curve, is above the green curve, which is g of x, right? So imagine has there's a gap between the two curves, right? Which I'm illustrating here. So as obviously the gap shrinks towards when it gets towards the point they cross over, but no matter what, before this point of intersection, the red curve is always above the green curve. What that means is, so if I call this point of intersection, say -3, and I call this other point of intersection 3, again, I'm not interested in the actual specific curve exactly, but I'm just trying to give an example. But let's say this first point is -3. Well, before -3, f of x is above g of x. Okay, so what we can represent that as an inequality when f of x is above g of x. That's saying f of x is greater than g of x. Okay, And so we can represent it as this. Okay, so f of x is above g of x specifically before my x is minus 3, which is this first point of intersection here, right? So before x is minus 3, as we move towards the point of intersection, again, look at the left side of my ruler here. The red curve will always be above the green curve, okay? So we can say f of x then is above g of x, which graphically means the f of x curve is above g of x when x is less than minus 3, okay? When we then do approach the first intersection here, well then what happens if we keep moving to the right? Well, actually, but then we meet the other point of intersection. But then what happens between the two curves then in this region here between the 2 points of intersections? Well, the green curve actually now taken over. Right, think about it kind of like a race. I don't know. But the green curve is now above the red curve, right, between these 2 points of intersection. So that means f of x is now less than f of x is below g of x. Remember, f of x is the red curve, g of x is the green curve. The red curve is below the green curve, so f of x is below g of x. So that means now f of x is less than g of x between these 2 points, minus 3 and 3, these 2 points of intersection. So we say f of x is less than g of x between minus 3 and 3. Okay, between the 2 points of intersection. Okay, so we can see that, right? Because f of x is now below g of x. But then what happens after they leave off at the second point of intersection? Well, then hopefully you see then f of x will then go up again and it'll be above g of x as we move away from the second point of intersection. So because then f of x is above g of x after 3, so when x is greater than 3, so after 3, f of x, the red curve, is now above the green curve. So f of x is above g of x again. So we say f of x is above g of x afterwards, okay? And so that's the whole, so that describes then these three values, these three um, different bits of information. They describe they describe when f of x is above or below g of x at certain points. Okay, and hopefully see, to reiterate once more, before the first intersection at minus 3, f of x is above the red curve, is above g of x. Then we move towards the first intersection point. Then between that and the second one, then g of x, the green curve, is now above the red curve. So f of x, the red curve, is now below g of x. So f of x is less than g of x. F of x is less than g of x. And then after we move off from the second intersection point, the f of x is now above g of x again. So it's greater than g of x. Okay. So that is the whole idea of this section. Is the idea that when we have two particular given curves, and we can plot the curve, we can sketch the curve f of x, g of x. We can determine one is greater than or less than by looking at when one curve is above or below another one. Okay, and that's the whole idea of this, right? And so yeah, this was a specific example, but the concept will apply, and we'll look at that. We'll look at that through more examples. Okay, so let's have a look at this example then. So we have example 12. We are given a line L1 with equation y is 12 plus 4x, which is drawn to us here, and L2, which has equation y is L squared, which is this quadratic curve here. The diagram shows the sketch, okay. It says part A, first of all, to find the coordinates of P1 and P2, which are here and here. Labeled that. But but that's the points of intersection, okay. So remember when we looked at in our first example, I kind of just given it, right? But actually we can work out exactly what these intersection points are that allow us to basically split up when one curve is above or below another. But we can find the points of intersection by just equating them together. So at these 2 points, first of all, that means they're equal to each other. So y is equal to 12 plus 4x, and y is equal to x squared, right? These two curves, they are equal to each other. So they've got simultaneous equations, which we looked at earlier on in the chapter. We know how to solve that, right? We can just put these two, substitute one equation to the other. So then simply x squared is equal to 12 plus 4x, right? Because the y's have to be the same, okay? But then that's just a quadratic equation, because then if I move everything to the left side, we get x squared minus 4x minus 12 equals 0, and then we can go from there. Well, I spot to solve it then. I could use the formula. I think I can spot I can factorize because I notice a factor of 12 is 6 and 2. And I notice I can do 6 minus 2 to get 6 minus 2 to get 4, okay? But then I want them to add to get minus 4 and times to get minus 12. So I need one of these numbers to be negative, but I need these two numbers to be minus 4. So I think we need to take minus 6 instead of 6. So then minus 6 add 2 will be minus 4. Minus 6 times 2 is minus 12. So that is our factors. So we can factorize x minus 6 x plus 2 equals 0. And remember, we looked at loads of factorizing examples in the earlier chapters if you need a refresh. But then we just set each factor to 0 to solve it, then x is 6 or x is minus 2. So that's the values then, but that's the x one, but that's the x values, but now we need the y values as well. Well, to get the y value, we just substitute it into either equation. So then firstly when x is 6, then y would be 12 plus 4 lots of 6. That would be, I'm just doing the calculator quickly. That would be 36, okay. Okay. And then likewise then, when x is minus 2 instead, y will be 12 plus 4 lots of minus 2. So again, I'm just substituting x into one of the equations to get the y value. That would be 4. Cool. Okay, so that's our solution, x, y, but it's asked for the coordinates. So remember, coordinates have to look like this, x, y. So we need to therefore write our answer as, therefore solutions are, well, 6, 36, and minus 2, 4. So that's the x, y coordinates, the x, y solutions. Okay, but that's the two coordinates, but it's told us to give the coordinates of P1 and P2. So what we then need to do is finally, which of these is P1 and which of these is P2, okay? And that's where we can look at the graph. So we have an x coordinate, well, P2, hopefully you can see is a negative x coordinate. It's on the negative x-axis. So clearly P2 is just going to be the right one. So P2 is going to be the coordinate minus 2, 4, and P1 is going to be the other one, right? It's going to be 6, 36, okay? And there we are. So that's the coordinates of those 2 points. Okay, then part B then, hence write down the solution to the inequality 12 plus 4x is greater than x squared. So that's going back to what we discussed at the start. So hopefully you recognise we actually sketched these two these lines, these curves on the graph already. This is almost like 12 plus 4x is kind of like f of x, and x squared is like g of x. We call them two different expressions of x, but we sketch these two sort of graphs already. They're on the graph for us. So what we're going to do then is when 12 plus 4x is greater than x squared, which that's saying the line L1, right? The line has to be above x squared. Okay, so let's have a look then. So let's go from left to right and let's see when the line is above the curve, right? The quadratic. So let's go from left to right. But hopefully, before we get this first point, P2, right here, when we reach there, beforehand, hopefully you see the curve, if we continue the line like that, hopefully see that the curve will always be above the line. Okay, so um, so that means 12 plus 4x L1 would be below x squared. Okay, so that would not be greater than. So before P2, the line is less than x squared. Okay. Okay, but then we reach P2. What happens then? So as we keep moving towards P1, well then hopefully spot at this point the line, right? The gap between the line and the curve. Well, the line is above the curve, right? The line is greater than the curve. So that means the line, 12 plus 4x, is greater than x squared between P2 and P1. Okay. So I'm going to say between P2 and P1. Okay, so hopefully you can see that. So that inequality here occurs between the 2 points. Okay, where the line is above the curve. But then what happens after we reach the second point, P1? After that point, if we were to continue on the graph to help you visualize, the curve then would always be above the line. Okay, um, so that at that point the line is below the curve, so that means 12 plus 4x would be less than x squared. Okay, so that would not be a solution there. So the only time that the line is above the curve, where 12 plus 4x is greater than x squared, is strictly between this first point here and this second point there. Okay, and hopefully you can see that. So the only solution, the only values of x when that happens, the only solution to this would be therefore solution when this inequality occurs, when 12 plus 4x is indeed above x squared, so greater than x squared, is between P1 and P2. But we know the x coordinates, right, of both these points. We worked that out in part A. P2 we know is minus 2, 4, and P1 is 6, 36. So the x values, right, is going to be between minus 2 and 6, right? And that's our answer. Cool. And there we are. So I guess visually, might take a bit of time to wrap your head around it, but hopefully that idea makes sense, right? The idea that essentially just looking at the points where the two curves are above each other or below each other, depending on the inequality. In this case, I want the line to be above the curve, okay? In order, because the inequality is greater than. Okay, and that occurs, so the x values then, remember we're solving for x because there's an x here. It occurs when the x value is between minus 2, which is at P2, and 6, which is at P1. So between those 2 points, that is when the line here is above the curve. Any other point, then the curve is above the line. So that's the other way around. That's not what we want. Okay, cool. Uh, and a last little comment to make with this. Hopefully you recognise this inequality here is a quadratic inequality. If we wanted to instead, we could actually solve that quadratic inequality using the method that we did last time. Right, we solved quadratic inequalities, but this gives us another way of solving it, right? Um, so hopefully you spot where this method can be useful. Okay. But cool. Let's have a look at another question then. And in this time, we are given the line L1 has equation 2y plus 3x is 6. And this other line L2, where given the equation x minus y is 5. The diagram shows a sketch of L1 and L2. Find the coordinates of P, the point of intersection. So again, the point of intersection is when they cross over. That's going to be here. So if I call that P, that's going to be this intersection there. So, when they cross over, that again means they're equal to each other. Remember we looked at simultaneous equations earlier on in the chapter. We make the two equations equal to each other and solve them as simultaneous equation when the two graphs cross over. So when they intersect. So when they intersect, then we can find that point. Well, x minus y is 5, and 2y plus 3x equals 6. Right, the two equations. Um, these are simultaneous equations because they are equal to each other. Okay, at this point P. Remember that. So then to solve it, we can solve it like we normally do with simultaneous equations. So I'm going to substitute, okay? So I'm going to rearrange the first equation to get x, say. So x then would be 5 add y by rearranging 1. So then I'm going to substitute x into the other equation to this rearranged to then just get y. So if I substitute x into the other equation, I then get 2y, add 3x, that's 3 lots of 5 plus y. That's going to equal 6, okay? Then I could expand it to get 2y, add 3 times 5 is 15, and then 3y is 6. Let's collect the y, so we get 5y. Then I'm going to move the 15 to the other side, so 6 minus 15 is going to be minus 9. But then y is a minus 9 over 5. Cool. So that's the y value, but then we need to find the x value as well, okay? Because remember, these come in pairs because there's an x and a y to solve. So to find the x value, we can just use this, right, that we used earlier, because that has our substitution. So then if y is minus 9 over 5, that means x is 5 plus y, which is going to equal 5 plus, well, 5 minus 9 over 5, right? And that will get me I put that in the calculator. It's 16 over 5, and there we are. So that's our x value. So that's our x and y value then. But then it said to find a coordinate. So remember, we need to give it as a coordinate, not just in this form here. Therefore, the coordinates of P, the coordinate is going to be x, y. That's 16 over 5 minus 9 over 5. Okay, and that is our answer. The point of intersection is this coordinate there. Okay, cool. There we are. So that's part A. Then for part B again, then it's saying, hence write down the solution to the inequality. 2y plus 3x is greater than x minus y. So then, hopefully then you recognize that actually we have x minus y in L2, and 2y plus 3x is the first line, L1. 2y is 3x is L1, and x minus y is L2. So we're saying simply L1 is greater than L2. Okay. So what we want to look at is when the first line L1 is above L2. So again, again, it's always handy to use a ruler, I guess, to help you visualize exactly when one line is above another. So let's have a look then. Let's read from left and let's move our way to the right. So as we go towards the point of intersection, hopefully see this line L1 here is above L2. Again, this gap here. Oh, for God's sake. This this gap here obviously means that L1 is above L2. Okay. And yes, so hopefully you can spot that right. So as we move towards the point P, but before it, L1 is above L2. And that's what we want, right? So that L1 and L2 occur when x is less than 16 over 5, okay? So that's the x value. That means that that inequality holds true, okay? Okay, but then let's consider maybe L1 would be bigger than L2 again. Let's then consider what happens after it reaches P. Well, after it reaches P, well then actually L2, this line here, now actually is bigger than L1, and it will continue to do so forever. Okay, so then this gap here between the two lines means actually after it reaches P, not before it, but after, as we move away from it, then the second line, L2, is now bigger than L1. So L1 is less than L2. Okay. L1 is now below L2. So L1 is less than L2. Okay. So that means the place where L1 is bigger than L2, L1 greater than L2, is before the point. So here, until we reach the point from the left, L1 is bigger than L2. Okay, this L1 is bigger than this L2. Okay, then it flips around after P. So that's the solution then. Before P, so before, because P is 16 over 5 for X, our solution is X is less than 16 over 5, because before it reaches 16 over 5, then that's when L1 is bigger than L2, which also is the same as this inequality here. Okay, cool. So hopefully you start to see the strategy and the idea behind it now. Let's have a look at another example. Okay, and this is a challenge one. It's actually pretty identical to the early example I gave, but it's nice to guess drum in what we've done to really reinforce what we've learned. So let's have a look. So this sketch shows the graph of f of x, which is x squared minus 4x minus 12, which is the black curve right here. And g of x is 6 plus 5x minus x squared, which is this red curve there. Part A then, again, it's pretty standard by the looks of it now. Find the coordinates for the point of intersection. So that's going to be here and here. How do we find it? Well, we need to put the two curves equal to each other. So f of x has to equal g of x, right? So the two curves, the two equations have to equal to each other. So then that means x squared minus 4x minus 12 is equal to 6 plus 5x minus x squared. Then we could just solve it, right? So I'm going to move everything to the right. Okay, so x squared plus x squared is 2x squared. To the left, sorry, move everything to the left. Move everything on the right to the left is what I meant to say. Then minus 4x and minus the 5x, as the 5x moves, it's going to be minus 9x. Then minus 12 minus 6 would be minus 18. And that's going to equal 0. Okay, then we can solve it. I'm going to use a quadratic formula. I don't like this 2 in the x squared. I can't be bothered to factorise it, if it even does. Let's just whack it in the calculator. So we have x is 9 plus or minus the square root of b squared. That's going to, oh God. B squared, which is minus 9 all squared. Minus 4 lots of 2, minus 18. Very, very rough side over 2 lots of 2. And that will give me our solution. Okay. So put that in a calculator. You should get the answers. X is 6. Or x is minus 3 over 2. Okay, cool. Okay, so that's the x values. It said there, well, it said to find the coordinates of the point of intersection. So we need x, y, a coordinate. Well, we need a y value. Well, y is all, well, y is equal to f of x, right? And y is equal to g of x because they're curves. So simply, we can substitute these x values into either curve to get the y value. So when x is 6, that means y at these points. I can substitute it in either equation here, f of x or g of x. Let's sub it into f of x. So well, x squared is going to be 6 squared. Minus 4x and minus 4 lots of 6. Minus 12. Put that in the calculator. You're going to get 0. Okay. And I guess that makes sense, right? Because 6 would be this point here, and it's on the x-axis, so it makes sense for y to be 0. It's always a good idea to check your answer and see if it makes sense. And it does build your intuition as well by doing that. Anyway, okay, so that's x is 6, y is 0. Then the other x value is minus 3 over 2. Then the corresponding y value be minus 3 over 2 squared, minus 4 lots of minus 3 over 2, minus 12, then that will equal, put that in the calculator. And if you want to, you could convert 3 over 2 to 1.5, but to make it easier, but I've just left it the fraction. That will get me minus 15 over 4. Cool. So yeah. So then that's the two x and that's the two solutions, right? To two pairs of solutions, x and y. But then it's one. We need to give the coordinates. Okay. So the coordinates will be 6 and 0. And minus 3 over 2 and minus 15 over 4. Okay, so the xy coordinates. So I'm going to say coordinates are, there we are. So that's the answer to part A. Cool. Part B, I'll do it over here. Then part B says from the set of values of x, which f of x is less than g of x. Okay. Okay, so remember then we apply the same strategy. So we want f of x to be less than g of x. We want f of x to be below g of x. So the curve f of x is below g of x. So remember, f of x is the black curve. So we want the black curve essentially to be below the red curve. Well, when does that happen? Well, you might be able to spot it at this point. Hopefully you become comfortable with it. But again, let's just move from left to right to consider every possibility. So before it reaches this first point here, the black curve is above the red curve. So f of x is greater than g of x. That's not what we want. Then as we move from this first point of this first point of intersection to the second point here, then hopefully see that actually the black curve f of x is now less than g of x because it's below. So f of x is less than g of x between these 2 points. And then afterwards, as we move away from the second point, the black curve is now bigger than the red curve as we go away. Okay, so f of x would be above g of x after the second point. So then, in summary, it's f of x is less than g of x. So f of x is below g of x between the 2 points only. Okay. So I'm going to say then f of x between the 2 points. So between the two x values, but we saw the two x values, right? Is minus 3 over 2 there and 6. So it's between x is minus 3 over 2 and x is 6. Therefore, as an inequality, so the range, so the values of x would be, therefore, that would be between minus 3 over 2, x and 6 as an inequality. Okay. So when x is between these two values, that means f of x is less than g of x, okay? And there we are. So between these two intersection points where x is between minus 3 over 2 and 6, that therefore in turn means f of x is less than g of x, okay? Find a point, then it says give your answer in set notation. We covered that extensively in the linear inequality section a few chapters back. We looked at how we write an inequality like this into a set notation. So you should remember that we can write that as a set, so a curly bracket, which means a set of the values of x such that, so x, and then this colon means such that. So the set of values of x such that, and then we just put our inequality in. So the values of x such that minus 3 over 2 is less than x, less than 6. And then we close it with another bracket. And that's our set notation, okay? I remember I looked at that two chapters ago, not chapters, two sub-chapters ago. We looked at linear inequalities and how you could transform that into a set notation, which is just a fancy way of describing an inequality, okay? It's the same thing, but you do need to know how to write in set notation. Okay, cool. So that's it then, right? So hopefully you spot what's going on with there. We're going to leave off with an exam question, okay? So let's get rid of this. So exam question then. We are given a figure 1 which shows a sketch of a curve C with equation y is f of x, where f of x is a cubic expression, so it's a cubic basically. The line with equation y is equal to k, where k is a constant, so k is just a number, right? Intersects C, the curve, at only one point. okay? Find the set of values of k, give me answer set notation. So set of values, again, implies there's a range, so we need an inequality. Anyway, so what's it saying is, we have this line, y is equal to k. Now you should know when k is just a number, so it could be y is 1, y is minus 2, y is minus 1,000, or so on. But what you should know, how would we plot that, right? Well, it would just be a horizontal line, right? That passes through one point, particular value of y. So it's going to be a completely flat horizontal line, okay? Um, okay, there we are. So if you imagine, so like this line here, that's y equals something. This line here, at this particular line, that'd be y equals 8, okay? Because the y coordinate here is 8. So that'd be y equals 8. Hopefully, again, that should be a brief reminder from GCSE. But that's what that means. What y is k means for some number y, it passes through one particular y value, and it's a flat horizontal line. So what that means is this y equals k. Okay, basically we need to see what values of y when we shift the line up and down to give different values of y. When does this line, which is why I'm using the ruler, right? This ruler basically represents this line y is k, okay? As we move up and down, okay? When does it only pass through C, the curve, once? Okay, remember that's what it's told us. So it's going to correspond to that point of being above and below again, kind of. It uses the same sort of idea. Um, okay, so we need to consider the points where it's only at one point. So again, let's start going. We can start going down actually if we want to. If we go down, imagine if this curve extends down forever, right? Because remember, these curves at the end of the day, they go on forever and ever, right? We have to have a cut-off point when drawing it, right? Because obviously we can't draw an infinite curve. Anyway, so if you imagine we extend it, but hopefully you recognise it's always going to pass through, no matter how far down we go. It's always going to pass through this curve once, okay? Until when? If we keep going up, it's going to have one intersection until it reaches this point here at 6. Then it's going to have 2 points, okay? Okay, so then it becomes 2 intersections. If you keep moving up, it's going to have 2 intersections, like here and here, right? Keep going up again, it's going to have 2 intersections here and here again. Always 2 intersections until it reaches this point, this other point here, 2, 8. And then afterwards, after we move from here, it then only has one crossover with the curve again. And it's going to be on this sort of area of the curve, right? And then imagine this curve extends up, like when we go down. If we go up, it's then going to keep only having one point of intersection, okay? So yeah, so basically what we need to do is basically summarize when this line y is k. So as we keep moving this line y is k, remember it's just different values, right? What values of y? So remember that this is the y-axis. So it's this line here, this ruler is simulating a line that passes through different values of y. So like here or here and here. Remember, um, when does this ruler, this line y is k, only pass through the curve once? Well, we just went over it. So before it gets to this point here, that's when it's only one intersection. And then after it leaves this point here, then there's only one intersection again. Between these 2 points, however, well, on these 2 points as well, there's 2 intersections, okay? So when we only want one intersection, it's going to be between this first point here that I've circled and this second point there, okay? So that's what we want then. So we want our y, our k equals y. We want our k value to be less than 0.1, right? Because then if it's less than, oh, this first point is going to keep going down when it only has one crossover. And we want our k value to be bigger than the second point here. and then afterwards it's going to go up. Okay, so that's what we want. Okay, so okay, what k values then? So it's going to correspond to the points of intersection again, right? That I've circled. So at the first point, at 1, right, the first point, k, well, k is the y value, isn't it? At this point 1, hopefully c is on the x-axis, which is when y is 0, okay? So that means k 0. And then at the second point, so at 2, k is going to equal to the y coordinate, which is 8. Hopefully you can spot here. 8. Okay. So then, therefore, the values of k, when this line y is k intersects the curve once only, is going to be, well, first it has to be less than 0, okay? Or, alternatively, when it's bigger than k is 8, because then that's when it has one intersection uh, at this point here, on this side of the curve as well. So those are the two values for k. That means that when we plot y is k, so when k is like -1, for instance, or when y is like 9, if we plotted those two lines, then it would only have one intersection with the curve. Okay, so those are two values of what of k then. Okay, um, so that's our solution then. That's it, right? So that's our solution. So those were the set or the range of values. Final question, final point. It says give your answer in set notation. So again, you should remember to write this inequality or set of inequalities as set notation. So that's then going to be the same as saying the set of values for k, such that k is less than 0. But remember, we can only put one inequality in a bracket in a set. Okay, what we do not say is k greater than 8, or we don't say k is less or k is greater than 8. Okay, we do not do that. Okay, it has to be only one inequality, so we have to leave it there and then introduce another bracket, so k such that k is greater than 8. Okay, remember that in set notation, the key idea is we only have one inequality a bracket. Okay, we do not join them together uh, like I just shown you. So then, so this is then set of values of k such that k is greater less than 0, but we want to say or. Okay, so remember or is this shape here, which means union, or it literally means or. Okay, again we went over this, but this is just a refresher reminder. Again, think back to the when you did Venn diagrams at GCSE. If we have sets A and B, we say A or B to be either or. Okay, so it's either circle A or circle B, which is where this U shape comes from. So the values of K could either be K is less than 0, which is the first set, or K could be greater than 8, which is the second set. Okay, so that's set notation. Again, make sure you are comfortable with that because they do like to ask you in exams to give you answer set notations sometimes. So don't throw away easy marks. Anyway, so that's it then. All right. I'll probably overcomplicate that a little bit actually, but hopefully you get the idea right now. The whole idea is that we can consider when two curves or two different graphs they are above or below each other, which allows us to then get an inequality. Okay. So when we consider if it one curve f of x is below or above g of x, then we can say f of x is less than g of x or f of x is greater than g of x, okay? Like the example we looked at, okay? And yeah, so I'm going to leave that there then. So I'll see you next time.